All right, we're going to start chapter 3, Matter and Minerals. This is actually two different slideshows. A slideshow covering matter and minerals in a broad sense, and then a slideshow covering matter and minerals in a specific sense. The second slideshow technically would go along with the lab that we do in class. However, this is online. We don't have an in-class lab. I'll offer something different at the end of this. I'll probably do that after recording as well. So first thing, this picture is real. That is an actual person in this picture, and those are actual gigantic crystals. This is a mine, I believe, in Mexico someplace. And yeah, that's not like a figurine. That's not a stage photo of any shape or sort. It actually exists. And it's someplace you can visit if you have the money, I guess. And this picture is a good job of indicating what these minerals and what this matter can look like. So, when I say mineral, what do I mean? How do I define mineral? Minerals are naturally occurring, not man-made. If something's man-made, we don't call it a mineral, we call it a product or something like that, right? Minerals are inorganic. You're not a mineral because you're organic. Minerals are solid. Liquids and gases are not considered minerals. So mercury is not considered a mineral technically. They have ordered internal molecular structure. They're not randomized in their structure. A mineral always has the same form of its atoms, and we'll get more into that as we go on. And lastly, a mineral has a definite chemical composition, meaning, again, those points 4 and 5 essentially tell you if you look at a mineral and you go to a different part of the world and find that same mineral, they're gonna be the same thing. That you're not gonna have variance in that way. So a rock, as opposed to a mineral, is an aggregate or mass of minerals. If you pick up something that's just one unique thing, one unique principal product, it's a mineral. If it's a rock, then you have many different minerals combined to form that rock, more or less. As of course, this is an introductory level class. The stuff's all more complicated technically than what we'll get into, but it will suffice. Quick chemistry precursor for you. Hopefully remember this from high school. Elements. Elements are composed of atoms, and they're the building block of, well, everything, but in our example, the building block of minerals. There are 92 naturally occurring elements in our world. Periodic table, I'm sure we've all seen this before, lists off those 92 naturally occurring elements, and on top of that, some artificial elements. Not can go too deep into the periodic table here, right? This is not a chemistry class. However, I'm assuming you know what an element is when I say element. We did say the elements need to be solid, not liquid or gas. So not all elements are minerals. For example, oxygen, not a mineral. Copper is a mineral. Atomic structure. What does an atom look like? Here we have a picture of the Bohr model of an atom, a technically outdated, but it still works, description of a atom. Atoms are composed of a central nucleus, which is made of protons and neutrons, positive and neutral charged particles, and then electrons surrounding the nucleus, which are negatively charged. All three of these main atomic particles combine to form the atoms, and the ways they combine form the different elements that we have in nature. These atoms can bond either chemically or ionically to create molecules and larger things, larger and larger minerals that exist. Chemical bonding is the formation of a compound by combining two or more elements, and ionic bonding happens when atoms gain or lose outermost electrons to form ions, and those ionic compounds are the orderly arrangement of these oppositely charged ions. Halite halite is an example. That's table salt, right? And that is a combination of sodium ions and sodium ions and chlorine ions, or chloride as we call it, in a 1-to-1 scenario. So when you eat your table salt with your food, it kind of looks like this picture on here. It's not green and purple, right? That's just an explanation. But it is an ionic bond of a metal and a nonmetal, sodium and chlorine, in ionic form to create what we eat today. Again, I'm really breezing through this stuff. Hopefully, at this point, you have at least a super, super basic understanding of chemistry well enough to where I don't need to go into details, right? Covalent bonds are another example of ways that minerals can form via elements combining. These happen when atoms share electrons to achieve electrical neutrality. Covalent bonds are stronger than ionic bonds, but they both occur in similar compounds. Bonds are seldom 100% ionic or covalent in character. We describe them as different, but in reality, things are more complicated. You could have covalent ion bonds happening within the same sort of molecules here. They give H2 hydrogen as an example of a covalent bond. So let's get more into the mineral side of things. Let's abandon the pure chemistry and get into some geology side. What types of bonding do we have? Well, first of all, we should talk about metallic bonding. Metallic bonding happens in a mineral when the outer electrons are free to migrate among the atoms. These metallic bonding is weak or weaker, less common than ionic and covalent bonds, and it produces, well, when I say metallic bonding, you're probably thinking metal, right? Something that looks metallic. Galena would be an example of that. You take a chunk of galena, chop it in half, the inside of it, the non-weathered part, the non-oxidized part, looks like shiny metal, right? That's probably because it's metallic bonding. Some of this stuff is just that easy. So that was super basic introduction, probably a bit too basic, but now that we have at least a foundation of chemistry, we can, again, as I said, transition more into geology. Let's talk about the physical properties of minerals. If you pick up a mineral, you look at a mineral, how can you describe it? Because I said before, remember, minerals are defined by the fact that they are unique in their composition, unique in their structure, unique in X, Y, Z. A mineral is a mineral, and that mineral is that mineral. So in order for us to describe what a mineral is, we need to have ways to describe it. The first one we will talk about here is luster. Luster is the appearance of a mineral in reflected light. What does the mineral look like when you look at it, right? The four descriptions we're going to talk about in this class are metallic, vitreous, I believe that's pronounced correctly, pearly, and earthy. And geology is useful in the sense that a lot of the terminology in geology is what it is. You don't need to go to your dictionary to figure out exactly what's going on, like in other classes. You ever took a biology class or a chemistry class, something like that, things can get pretty ridiculous. So if you ever take an anatomy class, geology is a bit more simple. If I say something's metallic, that's because it looks like it's made of metal. Example, the galena we talked about previously. That looks metallic, so we call it metallic. Pearly looks like pearls. Earthy looks like earth, right? Dirt, stuff like that. Vitreous, kind of a weird one, but it's a glassy luster. Not going to necessarily go over examples of each of these because, I don't think you really need to, right? If you pick up a mineral and it looks like dirt, you'd say it looks dull, earthy. Color is another principal definition of a physical property of a mineral. And this actually breaks the trend I just talked about. I said all the minerals kind of look like themselves. Color is a unreliable yet still definitive way to describe a mineral, in the sense that here we have 4 examples of quartz that all look very different but are all actually quartz. Color usually has to do with, for example, quartz, something happening to the quartz to give it that color, such as radioactive decay or the surrounding rocks changing colors. But again, quartz comes in several colors, but we know what those colors are. So one of the definitions of quartz is its color. You can't always define a mineral by its color, but the color is defined by the mineral. I hope that makes sense. Many minerals are found in the same color. Some minerals are found in more than one color. There are many minerals out there that are white, including quartz. So if you find a white mineral, that doesn't mean you have quartz, but a white quartz is still quartz. Streak. Streak's a fun one, commonly used with pyrite. Streak is what color a mineral looks like when you crumble it down, when you powder it, as opposed to color, which is the color when you held it in your hands. If you scratch it, the color may change. Again, pyrite is an example of this. Pyrite is fool's gold, right? Pyrite looks like gold, but if you crumble it, it crumbles black. It loses that gold color when it powders. We use things called streak plates, is just ceramic plates that we rub rocks on to find their streak color. So some minerals have a unique streak from their color, some minerals do not. Hardness. Again, nice thing about geology, if I say the hardness of something, I don't need to explain to you what hardness is, right? Hardness is, well, the resistance of a mineral to abrasion or scratching, how hard the mineral is. We use in geology a Mohs hardness scale or a relative hardness scale to describe how hard something is. It goes from 1 to 10, 10 being the most hard, diamond, 1 being the least hard, talc, like literally crumbles in your hand. Will crumble under abrasion or scratching. And this relative approach allows us to more easily classify rocks that may appear similar in other ways. Quartz and calcite look pretty similar to each other. If you ever pick up a rock where you're walking around and you think it's some quartz, there's a good chance it's actually calcite because the two look very similar. They both have this white kind of crystally looking structure to them. However, if you have a penny on hand or a small knife and you try to scratch up the rock in question, if you're able to scratch and chip apart the rock that you found, it's calcite. If you're not able to scratch or chip apart that rock, it's quartz. Quartz is a lot harder than calcite. The definition based on, again, the chemical structure and the atomic structure of the rock. We can, of course, do an absolute scale comparing hardnesses, but in a field sense, that's not as useful. You don't really want to remember all these different various numbers for how hard something is. Most hardness scale works better off the top of your head, right? Cleavage. Cleavage is the tendency to break along planes of weak bonds. Cleavage defines how a rock will break. If a rock is going to break, how it breaks is indicative of the individual rocks. Cleavage can come across in various geometric shapes, different planes along the mineral. There are some examples like biotite, for example, and mica, biotite mica, that cleavage is one of its defining characteristics because it comes off very planar, very flat. Mica breaks off essentially in pieces of paper. The cleavage is the defining aspect of mica. If you find a rock out in the wilderness that's very flat, and you can literally, as I said, pull it apart like a book, you found mica. You know that because that is a distinguishing property of the cleavage is the distinguishing property of that particular mineral. A is what I'm talking about here. Muscovite is, that's mica. You can also have cleavage break at different angles. And again, all these are examples of if the rock's going to break naturally, it's going to break along certain edges. Halite likes to break in 3 different directions at 90-degree angles. Halite likes to come off in cubes. Calcite likes to break off in 3 directions as well, but it doesn't like 90-degree angles. This has to do with the way the atoms are formed within the individual minerals and allows us to define the rocks in certain ways. Because again, D and E look pretty similar, but the fact that D is more cubic and E is less cubic allows us to distinguish between them. B and C, again, feldspar and hornblende can look very similar in the field. But if you break off the rock and it breaks off in nice 90-degree square looking right angles, you have a feldspar. Hornblende doesn't want to break off in 90-degree angles. And as I said before, mica, biotite and muscovite mica are the best example of this because they break off like literal pieces of paper. Fracture. If a rock does not necessarily have a preferred cleavage plane, we call it having a fracturing. And again, fracturing is something that can be unique to the rock. Here we have an example of conchoidal fracturing, and these sort of looks like someone scooped, like ice cream scooped out a piece of the rock when it broke. That's something this rock will do. If you continue to break this rock, it's going to fracture in these semi-random events like that. So again, fracturing cleavage to find the same things. What cleavage says we're going to do this geometrically, fracturing says we're not going to do this geometrically. Specific gravity, it's essentially how dense the rock is. Some rocks, some minerals, so I keep using rocks when I mean minerals, I apologize. Some minerals are heavier than others. Talc is very light. Pyrite is, well, pyrite's not a mineral, but talc is very light. Copper is very heavy. If you're walking around and you pick up a rock and you wonder if it has copper in it, look at the rock and feel it. Does that rock feel heavier than it looks? If it does, you probably have copper in that rock because copper is very dense, has a very high specific gravity. Crystalline structure is another definition of a mineral, another property of a mineral. And before I go any further, I said at the beginning, rocks are essentially a collection of different minerals. So rocks can share these properties because the minerals they're composed of share these properties. So if you look at this stuff and you're saying, hey, I've seen rocks that have these specific pieces and parts of them, yes, that's exactly correct. So crystalline structure, the shape or form a mineral crystal takes when it grows in an empty space. If you're going to let the crystal grow, what's it going to do? Well, if it's going to grow in squares, we talked about that already, that's halite, that's salt. Salt tends to grow in these cubic crystals shown in D. Asbestos grows fibrously. Asbestos is a mineral, in case you didn't know. And funny part, asbestos is actually safe to eat. Asbestos is dangerous when it gets in your lungs, but it's not dangerous otherwise. My geology professor, when I took the equivalent of this class way back when, would always eat a chunk of asbestos in front of us when doing this demonstration because it's just a mineral, right? Some crystals grow bladed, some crystals grow banded. There's a wide variety out there. It's all very cool and very interesting. If you get the opportunity, I'm going to highly suggest you visit a mineral museum at some point in your life. Just seeing the complexity that is the natural world is really cool and fascinating. And you end up taking away a lot more than you think you would. You'll have a good time, trust me. So what are other physical properties of minerals? Less common ways to distinguish minerals. Some minerals are magnetic. Magnetite and hematite would be examples of this. And that essentially is you stick a magnet to it and the magnet sticks. There you go. You have a magnetic mineral. You know it's magnetite or hematite as opposed to some other rock that may look or have a similar hardness. Some rocks react to acids. For example, calcite bubbles under hydrochloric acid. If you drop a little bit of hydrochloric acid on a rock and it bubbles, it's calcite. If you drop some hydrochloric acid on quartz, which can look very similar, it won't bubble. Therefore, you know it's not calcite. Malleability. Copper is a good example of a malleable rock. Malleability essentially is ability to bend without breaking. That's a good way to describe it. And what it does is allows you to tell that you have a piece of copper there. If you ever pick up a piece of copper off the ground stuck in a rock, you're able to bend the copper around. You can't do that with some other minerals. Silver also has a malleability nature to it, but I believe like iron or sulfur or something like that doesn't. You can't bend it. Taste. Some rocks have a taste. I told you before, halite's table salt because halite tastes like table salt. Geologists actually go out there and lick rocks sometimes because halite looks so similar to quartz, to calcite, to a few other minerals that if you don't know what it is and you don't have, let's say, a knife on hand or a bottle of hydrochloric acid for some reason, you can just lick the rock. And if it tastes like salt, That's because it's salt. Sulfur, if you've ever been to a geyser or Yellowstone, something like that, you know sulfur has a very rotten egg smell to it. That rock just smells that way. And elasticity, as I talked about before, different from malleability. Mica would be an example of something that's elastic because it's basically a piece of paper. There are nearly 4,000 minerals that have been identified, 4,000 individual unique minerals with each their own table of properties that are exclusive to that mineral. In this class, if this was in person, we'd be spending time IDing these minerals. If you're taking this in the online component, which you're doing now, obviously, we're going to do something different about that. I'll let you guys know at the end of this presentation or in the emails how that's going to work. We have rock-forming minerals. These are very common minerals that make up most of the rocks on Earth. The rocks that are formed, those minerals, are composed mainly of 8 elements. And these 8 elements make up 98% of the continental crust. Of those two, silicone and oxygen are the most common. Silicone and oxygen account for the vast majority of the rocks we see every single day. You pick up a rock, I'd be shocked if you pick up a rock and there isn't silicone and oxygen atoms in its composition. I really would. I don't know where you're living if you're picking up a rock without one of those two in it. There are other elements, as I said, right? Iron, potassium, magnesium, sodium, calcium, aluminum, etc. But those all usually are in molecules or compounds alongside silicone and oxygen to form what we see. And even though there's just these 8, that doesn't seem like a lot, there's a lot of variety within these elements, right? Go back to chemistry. Think about all the different ways you can combine hydrogen and oxygen together. So, H2O is water, H2O2 is hydrogen peroxide, right? Just add another atom in there, and all of a sudden, what you used to drink now kills bacteria in a cut on your arm. So, mineral groups. If I'm going a bit fast, feel free to raise your hand, say something, ask a question. I don't think this stuff is too out there. And sadly, this is best done in person, so I can show you a piece of mica and you can see it looks like paper, but we're doing the best we can here, right? Silicates. Silicates are a group of minerals. Group of minerals means, right, it's sort of, again, in the periodic table, you have your families and your groups. That is a way to categorize elements that have similar features or functions. Mineral groups work the same way. Silicates all have silicone and oxygen in their chemical composition, but silicates all behave in similar ways under similar circumstances. If I give you a rock and I tell you it's a silicate, and you know what a silicate is, you know things about that rock that I don't have to explain to you, right? Silicates are the most important mineral group. Most important is a weird phrasing, but silicates are very common. They comprise most of the rock-forming minerals on Earth and are the most abundant group. So those two bullet points kind of say the same thing, right? As a result of the large amount of silicone oxygen in Earth's crust. The basic building block is the silicone-oxygen tetrahedron molecule, wherein 4 oxygen atoms surround one much smaller silicone atom and are combined via strong covalent bonds. Looking like this. You have a molecule, SiO4, 4-, that with this basic structure, this basic shape, a vast majority of the many different rocks and minerals we see in the Earth arise. This basic structure, this basic shape, sort of allows the world to exist the way it exists. It's very, very important chemistry. Those silicates, those tetrahedrons that were shown here in cartoon form, link together to form various structures, including, again, the isolated tetrahedra, chain, sheets, complex 3D structures. You can Lego piece these guys together to form many different silicate form silicate structures, and then those structures go on to make the rocks and minerals that we live with on a day-to-day basis. Here's an example of that. Olivine, augite, hornblende, biotite, feldspar, and quartz all are silicate minerals. They all have the same basic foundation, the same basic molecular structure as shown in that third column. However, that being said, the way they form, the way they do what they do, and the other elements they play with allow a wide variety of different minerals all under the same group of silicate. Hornblende and augite have similarities, also have very big differences. They are composed of different elements beyond the silicone and oxygen atoms. They chain differently, making them having different cleavages, different hardnesses, etc., etc. Although augite and hornblende are actually very similar in hardness. And furthermore, the other cool thing is, as long as you get deeper in geology, you will notice when you see certain rocks, that's usually indicative of other rocks and minerals surrounding it. Olivine shows up a lot with metals. If you're starting to see a lot of olivine, you're probably going to find a copper or an iron or a silver around that. Usually, if you pick up a piece of copper, you look at it, there's some green someplace on it. That's not the copper oxidizing. That's olivine or serpentinite or something similar that is growing alongside the copper. So, as I said, we have these tetrahedras, these silica tetrahedra compounds, and they, as was shown back here, form at a -4 charge. Right? Again, you have to go into oxygen and silicon, the common ions and things like that. So tetrahedras form at a -4 charge. Metal ions with a positive charge are needed to balance this out. So these silicones, as shown here in the mineral formula, will notice the silicone, the Si and the Os, tend to form with a lot of metals, as I said previously with the olivine copper association. Because that tetrahedra has a -4 charge, the atom wants to be balanced, so it's going to hook up with these common metal cations, iron, magnesium, potassium, sodium, etc., to balance out. Again, if you don't remember your chemistry from previous classes or from high school, this may seem a bit convoluted, confusing, but the takeaway from all this is these silicates tend to form with metals and other minerals we like because they want to be neutrally charged. The linking silicate tetrahedras can form covalent silicone-oxygen bonds. And these are typically stronger than ionic bonds, as I said before. And the linking of these tetrahedrals control the cleavage or hardness of the mineral. As I said previously, that tetrahedron, that cartoon we showed, can work with many different other elements and combine in many different unique ways to produce a wide variety of minerals, the wide variety of the world that we exist. Quartz is a silicate. Quartz is very strong, has a very distinct cleavage plane, very distinct looking crystals. Talc is also a silicate, and it crumbles. You know, you've had talc powder before, right? Smash that talc powder up in your hand, you almost have a rock of talc. It's just that weak. So, as stated before, these all are within the same group. They all seem very unique and different from each other, but in fact, they all can tell us the same sort of information, which is cool. Jessica, do you have a question? Oh, nope, I guess not. So let's talk a couple common silicate minerals. Feldspars. Feldspars are the most common. You can see these all over the place, all over the time, everywhere. You look at this, what do you say? Well, that looks like a dirty rock, right? So it probably has an earthy luster to it, and you would be correct. Technically, they're not that interesting, not that cool because they're so common, but they allow the world to be built in the way it's built. Labradorite's probably a bit more interesting because it's got that nice, cool blue color to it. But these all chemically are very similar. Quartz, we all know quartz, very abundant mineral. Yeah, I will tell you right now, quartz does not have some special magical, mystical component to it. If you put a piece of quartz on your headboard of your bed, you're not going to have better dreams. I'm sorry. It's just some silicone and some oxygen. I apologize if I've ruined your life now. Important non-silicate minerals out there, right? Silicone and oxygen combine to form a lot of what we have, but that's not the entirety of it. Oxides, sulfides, sulfates, native elements, carbonites, halides. These are all different chemical combinations, different elements that combine in common forms to produce what we have in front of us. And if I say halide, that means something. And if I tell you this rock is a halide, you can know certain things about it before I give it to you. If I tell you this rock is a sulfate, you know certain things about it before I give it to you, right? These are groups. These are different ways to classify minerals in a broad sense. As shown here, and some economic uses of them. Cool story. Halides, right? Salt, fertilizer, stuff like that. Oxides, ores, corundums. I'm not going to get too deep into this. If you take any more geology classes past this, those geology classes may focus on certain specific parts of these. That would be covered in depth at that point. However, as we go forward, if I tell you a rock has some silicates in that, or some sulfites in that, this is where that's coming from. Ore is another way we can define minerals. Ores are useful metallic minerals mined at a profit. An ore is an ore. Iron ore, I'm sure you're aware of what iron ore is. So that is technically the end of this slideshow. However, I want to share a different slide and go over that as well. That goes a bit deeper into the different minerals so we can have a better understanding of what we're talking about here. This shouldn't be too long. It's actually shorter than the last slideshow. And it will give you some pictures to associate with this stuff. So we talked about silicates, talked about silica tetrahedron, things of that nature, most abundant mineral group, etc., etc. Cool story. Seen this picture already. Here's a better close-up view of the different ways these tetrahedrons, these triangles can combine. And keep in mind when you're looking at this, these are actually in real life three-dimensional structures. They're not triangles that are connecting, they are pyramids that are connecting, right? So we can talk about all those different silicate materials and give a nice bullet point-esque definition of what's going on here. For example, quartz. If I tell you something is quartz, you know these four components are true. You know it's harder than glass. You know it doesn't necessarily have a specific cleavage. Some quartz does, some quartz doesn't. You know it has a glassy luster, and you know it tends to be at least translucent, if not transparent. That is the way quartz functions. Yes, quartz very commonly produces this cubic structure, but it's not necessarily a definition of every quartz crystal. That is definition of like quartz growing in an open air environment more so. As I said, quartz is one of those things that's very, very, very expansive. There's lots of different quartzes. Oh, question here. So native elements of minerals that consist of only one element on the periodic table. That's not a bad way to think about it. Let me go back to that list. Yes, I'd say that would be a good way to define native element. It's not the only way to define native element, I believe, but there are certain minerals out there that exist just as isolated atoms. That is possible for some atoms to do that, not all atoms. You're never going to find oxygen by itself, for example, but gold, copper, sulfur, stuff like that do exist in that way. Yes, that is correct. Let me go back to that slideshow. There we go. We talked about potassiums and feldspars. Plagioclase and potassium feldspar are both very, very super common. Kind of hard to tell the difference between them sometimes. Potassium feldspars tend to be pink, but not always. Easily scratched. Plagioclase feldspar tend to be white, a bit harder usually. Biotite and muscovite micas. This is the paper I was talking about. You see that guy literally lifting up a sheet of mica because mica sheets out in that way. Very soft. You can look straight through it. It's transparent. That's cool. And again, in class, I'd give you a piece of mica to play with so you'd understand a bit better. Hopefully, when we get to the lab for this week, you'll be able to experience some of this. Augite, very common, dark greenish hue mineral, 90-degree cleavage, hard. Hornblende, similar, except it's more of a black. Unique cleavage planes. Hornblende breaks at, it kind of looks like it's a bunch of rectangles, but those rectangles not the correct angles. It has like cleavage at 124 and 66. Very unique cleavage breaks. If you pick up a rock and it has long lines of a hard black mineral in it, that hard black mineral is hornblende. And it tends to look pretty cool. Olivine, as I said before, is a very vibrant green crystal. Pretty hard, shows up very commonly on rocks. It almost kind of looks like moss sometimes until you touch it and you get a cut in your finger because it's so hard. Garnet. Interesting thing about garnet. Garnet, we usually think of as a gemstone. However, garnet is not always a bright, vibrant gemstone. The best way to define a garnet is actually via its hardness more so than any sort of luster or color. Garnet is a very, very hard, dense rock. Kaolinite is an example of a talc-like substance, very, very, very soft. White cream color, very true in that regard. Talc, as I said before, is super soft. It's actually oddly greasy. If you ever get a chance to play with some talc, you can be surprised that it doesn't feel like a rock. It feels like, well, as I said before, it feels very greasy. Like you feel like you need to wash your hands after you touch it. It's very interesting that way. And it's a good way to distinguish talc from kaolinite, which is a very chalky, almost like a touching a Dorito. Cool. Those are the common silicates. Let's get into carbonates. A different group, different main minerals involved in the creation, but as said before, wide variety. Calcite is a carbonate. Calcite does not have silicone in it, as opposed to quartz. The two look very similar, right? These pictures and the quartz pictures I showed earlier look similar, have similar breakage, similar crystal structures, but in fact are very different. Calcite comes in a ridiculous amount of colors, tends to break and form crystals that are not at right angles, as said before, and is actually very soft. So if you pick up a rock, you don't know if it's calcite or quartz, and you don't happen to have your hydrochloric acid on you at the moment, scratch it with your finger. If you can scratch it, you have calcite. Calcite has a double refraction given the orientation of the atoms within the mineral. You need a really, really pristine example of calcite to get this to happen, though, right? You're not really looking through a lot of these crystals here, but that is something that it does do. Again, given that non-90-degree cleavage. Sulfates. So as I'm going through this, as I'm doing less and less of the individual groups, there are a lot of carbonates out there, a lot of important carbonates. Calcite's just the best example I'm doing at the moment. Gypsum is an example of a sulfate. Gypsum, I believe, is what we use to make like drywall and stuff like that. And it kind of looks like kaolinite, right? It kind of has that look of those silicates that we talked about before. However, since gypsum is a sulfate, it is a different chemical composition, different structure. is in fact harder. You can't exactly, it's not as brittle. You can't rub gypsum in your hand and expect it to crumble the same way that kaolinite or maybe talc would do. Halides, this should sound familiar. This derives its name from halite, which is a group, as I said before, sorry, not a group, a column, a family on the periodic table. It's the salts. Halite, you know it's halite and not quartz or calcite because you taste it and it tastes salty because it's actual salt. Fluorite being an example of this, right? Go to 7A on the periodic table, run that down. All the elements, all the minerals and rocks produced from those elements fall in this category and all have very similar structures to them, very similar components to them. Fluorite is another one of those, is this quartz? I can't tell because you can get examples. This pink quartz here, this pink fluorite here looks an awful lot like pink quartz or pink calcite. How do you tell the difference? Well, it's softer than quartz, it's harder than calcite, and it has other various structural components to it. Fluorite, I do not believe tastes like salt. Sorry. But this is also, right, where we get a lot of fluoride comes from fluorite, which gives you nice, bright, happy teeth. Sulfides, sulfates, that's a different of oxygen count. It's more of a chemistry component. Galena is an example of a sulfide. This is the pristine example of a metallic luster. Very cubic, very dense. And galena is one of those good examples of a rock with a streak, because if you scratch this on, let's say, a piece of ceramic, it does not keep that luster upon streaking. It loses that glow, it loses that sheen. Pyrite, again, same family, similar properties, right? Metallic structure, different streak, different hardnesses, however, but similar cubic structure. Pyrite crystals grow in ridiculous organizations. You get a big piece of pyrite, it looks almost like it's like a sci-fi trophy or something like that. They're really cool looking. Safflerite, this is a unique rock. This is a rock that's simultaneously hard to find, but kind of everywhere. It's a very it's a very soft rock for the look of it. It looks like something that you could, it looks very dense, very hard. However, safflerite can break rather easily, can be cut rather easily. A good way to tell safflerite versus XYZ other mineral is with streak. Notice here, all the sulfides, a key characteristic of them is streak, as said before, right? Safflerite gives a yellow streak to it. It may look kind of brown amber color, but its streak is notably different. And streak is not something also that other rocks necessarily have. Potassium feldspar does not have a different colored streak to it. Finally, we can get into some oxides. Corundum is a good example of oxide. Corundum is very hard. Corundum is, I think, a 9 on the most hardness scale. If you can't scratch it, no matter how hard you try, unless you take a dive into it. And corundum also always comes up with these hexagonal prisms. It grows in 6-sided shapes. Very interesting. So if you find a 6-sided mineral out while walking around, and it seems like super hard, like your knife can't get a good scrape on it, you probably found some corundum. Very cool mineral. Very dense too. Very high specific gravity. Very heavy. Magnetite. It's magnetic, right? It kind of looks like galena to a certain extent, right? Except galena is not magnetic and magnetite is. Hematite is similar to magnetite, except it doesn't have the magnetic luster to it. It's reds and browns and things of that nature, but it still likewise is magnetic. They say it's less magnetic than magnetite, but it varies on the rock, really. It's not a perfect way to describe it. Distinguishing magnetite and hematite is more so about a luster than about a magnetism. And again, as we come down here, we talk about our native elements, which consist, as Cassidy pointed out, of mostly all one element. Copper, I assume I'm not going to have to explain the native elements very much. Copper, graphite's made of carbon, right? Sulfur is made of sulfur. However, I will stop here and notice that just because the native elements all comprised of essentially the same atom does not mean they only show up in one way. Sulfur has a crystalline structure. Sulfur has a non-crystalline structure. Yeah. The non-crystalline structure is probably the one you see more often, but a sulfur crystal is really cool looking, right? It smells. I wouldn't necessarily want to sit in the room with a big sulfur crystal. That would not be a good odor, but they exist. And quartzes and calcites, and I think even fluorides can look yellow too. So again, how do you distinguish them? Give it a sniff. And that comes to the end of this presentation. So I'm going to pause the recording, and then if you guys want to ask any questions, feel right ahead. And then, as I said before, this will also be posted on YouTube, so you can watch it.